Okie dokie artichokes. Here is Mapoy with a fresh new look on her review videos. This is how I run my content review. I probably did a 1D kinematics video from last year, but it didn't look as great, so I'm going to start over with a fresh new look. And so let's start with 1D kinematics. And here, the topics I'm going to cover in this video are distance and displacement, speed and velocity, acceleration, kinematic equations, and freefall. If you're looking for motion graphs, you probably need to check out a separate video on motion graphs. I'll probably put a link in the email I'll send you guys about that. And let's begin with distance and displacement. So here, two different quantities. Distance talks about how far an object has traveled along its path, whereas displacement is about how far it is removed from its starting position. So, what does that mean? Don't they talk about the same thing? Not exactly. So if you have a person going up this way, and he moves this way, and he goes down this way, and if we attach numbers to that, so let's say he goes 10 here, he goes 12 here, and then 5 here. So the distance is how far the path actually took. So you add these up, 10 plus 12 plus 5. In our example question here, 10 plus 12 plus 5 will get us 27 meters. But the displacement is all about from start to finish. So you started right here and then you move up to here. So if you probably had to make a triangle, use Pythagorean theorem and such, so you get that this little triangle right here is 5 and then 12 here, then you got to use Pythagorean theorem and you'll realize that the answer happens to be 13. Wow, I made up these numbers on the fly and it came out quite evenly. So this right here, you're 13 meters away from your starting point when you end up. But the distance is how far you actually traveled physically going around obstacles. But displacement avoids obstacles. It goes the straight line path from start to finish. All right? But in most of the scenarios we look at, distance and displacement will mean the same thing when only traveling in a straight line. All right? So if you're only traveling this way, 10 meters, and you end there, that's just a straight line. They mean the same thing. You move 10 meters, and you're also 10 meters away from your starting point. So that's the only scenario where they're the same. The previous example I started out with, when talking about the differences, you have changes in direction. So that's the time when they are different. Now, I went about talking about these two without even saying what their units and variables are. So the unit, we measure distance and displacement, is meters. And then the variable is d, to represent both of them. Next, we move on to speed and velocity. So if distance and displacement ask how far, now we're talking about how fast. How fast are we moving? So this is a rate of how quickly your distance changes. So this is a rate of distance over time, or displacement over time. So meters per second is our unit. And the variable we use for both of them is v. V for velocity. Speed and velocity also equal each other in the scenario where distance and displacement are the same. So this is in a straight line. So they're not equal to each other when you start to change directions. Okay? So speed is related to distance over time, because they're both scalars. And then velocity, average velocity, relates to displacement over time, because they're both vectors. So let's talk about a basic constant velocity example where an object travels at 15 meters per second for 8 seconds. So the relationship between these variables is v is equal to d over t. That's our constant velocity equation. So this right here is your velocity, and this is your time. So that means we're looking for distance. How far did the object travel within this time period? So going 15 meters per second equals d over 8 seconds. D is then equal to 8 times 15, so that is 120 meters. So that's an example of questions you might see where they give you 2 of the 3 variables and you got to solve for the third missing one. Okay? So this is an example where distance and displacement are the same thing because we're traveling in a straight line. Now what happens if you're not traveling in a straight line? So what if you go 90 meters west and then 30 meters east? So then your displacement, you take the difference between them because you're going in opposite directions. Displacement is equal to 60 meters. And you travel for a time interval of 10 seconds. So what is your average velocity? So average velocity is then equal to displacement over time, so 60 meters over 10 seconds. This would equal 6 meters per second. Now if they ask for speed, then average speed, so you need your distance. So taking into account the same 2 numbers, you travel 90 meters west and then 30 meters east. Your distance then is equal to 120 meters. So over the same time interval of 10 seconds, your average speed is equal to 120 meters over 10 seconds. So you travel 12 meters per second, twice as fast. So that's in a scenario where speed and velocity are different because distance and displacement are different. And that relies on changing directions. If it's just a straight line, then you could assume they're the same thing. So let's say you have 2 cars, A and B, set at opposite ends. One is going 15 centimeters per second, the other is going 7 centimeters per second, and they're going in opposite directions towards each other. And we want to figure out their collision time. How do we figure that out? So let's think about it this way. Car A, going 15 centimeters per second, it moves forward 15 centimeters in 1 second. Car B moves forward the other way 7 centimeters per second. So if both are moving simultaneously, so 15 here and 7 here, all together, they're moving forward together, covering 22 centimeters per second. So the velocity of both cars together, 15 centimeters per second plus 7 centimeters per second, you're going to get 22 centimeters per second for both cars moving together at the same time, forward towards each other. And so if we know that velocity is equal to displacement over time, and we know they need to cover a distance of 100 centimeters together before they collide, 22 centimeters per second equals 100 centimeters per second. So by the time they collide, they will finish that 100 centimeter difference together. You get 22t equals 100. T is equal to 100 divided by 22, and that's 100 divided by 22, that's 4.55 seconds. So this is the shortcut. When you have 2 cars opposing each other, heading towards each other and about to collide, you're going to add their speeds together to figure out how fast they're moving together along the same distance. So 100 centimeters divided by 22 centimeters per second gets you 4.55 seconds before they collide. Now here's a special kind of problem you might rarely see. So again, we have 2 cars. So let's say they're about 50 centimeters apart. This one is moving forward 5 centimeters per second, and this one's also moving forward 10 centimeters per second. So they're going in the same direction, but the faster one's behind. So how much time will it take for the faster car, A, to hit the behind of car B? So this is a different scenario, but we're going to apply the same mindset here. So in 1 second, car A moves forward 10 centimeters. Meanwhile, car B moves forward 5 centimeters. So I'm going to use a different color. Car A moves forward 10 centimeters. So it'll be 10 centimeters closer. So there's a difference of 40 now. But this, at the same time, will move forward 5 centimeters. So it'll be a difference of 45 centimeters. So each second that passes while car A moves forward 10, the car B moves forward 5. So overall, that difference is 5 centimeters per second to compensate for both cars moving together the same direction. So because they're going in the same direction, you got to take the difference. So altogether, they're trying to cover that 50 centimeter distance 5 centimeters per second at a time. All right? And we're still going to apply the same idea. V equals d over t. T equals 50, and so it's going to take 10 seconds before car A hits the back of car B. So it does take more time when you have a car catching up to the other car. Whereas in the previous scenario, you saw two cars heading towards each other, so that's going to happen quicker versus this scenario where one car has to catch up to the other. So now we're going to move on to acceleration. And I've noticed that there's a common misconception, I guess, with speed, velocity, with acceleration. These two are different things. So I guess if people still get confused, that means I need to do a better job teaching and explaining it in class. But anyhow, here's me trying to rectify this. So acceleration, you're going to ask yourself, am I getting faster or am I getting slower? Sorry. Am I getting faster or slower? That means when I'm changing my speed, am I changing it to go faster, going from 0 to 10 to 20, or am I going slower from 10 to 0? And so the unit we use is meters per second squared, so that each second that passes, you're changing your velocity. And so the variable we use is a, and the direction. So the direction I'll get into for a moment later. So acceleration is marked by this equation, change in velocity over time. So you need two velocities. If you're changing your velocity, that means you have an acceleration. But if there's no change, if you have a constant velocity, means no change. That means 0 acceleration. Now talking about direction, you need to focus on the direction of the arrows. If you're moving to the right and you're speeding up, that means your acceleration is also directed to the right. That means you're moving to the right and you're pressing on the gas pedal, so you're speeding up. But let's say you're also moving to the right, but your acceleration is directed backwards. That means something is pulling you backwards. This means you're slowing down. So something like a negative acceleration doesn't necessarily mean you're slowing down. It could also mean you're speeding up in the other direction. So sometimes, for simplicity of calculations, you might even use a negative sign to indicate you're slowing down as well. So when acceleration is involved, the following equations must be used. So these three are on the reference table. These three are on a reference table, and notice how each of them involve the use of A and VI. So you can't use any of these equations unless you have an acceleration. And when acceleration is involved, you're going to use these equations. And the keyword you need to look for is two different velocities or the word acceleration. But if you have a scenario where velocity is constant velocity, then you don't have acceleration. And the key to solving these kinematic problems is to identify what you're given and then see which equation will only leave you with one missing variable. If you're left with more than one, if you have two missing variables or even three, then don't even bother using it. You need to find something else or go back to the problem and find another piece of information. So that leads into this example, when acceleration isn't given, but you need to find something else. So we need to figure out how far the object is traveling. So that's a distance, that's what we're looking for. But they also gave us two different velocities and a time. VI is 8 meters per second. VF is 16 meters per second. T time is 10 seconds. We need to find D, but there's no equation that'll leave us with one missing variable. So that means we need to find acceleration first. So this is an example of a two-step problem where you need to find acceleration first before what you need. Equals 0.8 meters per second squared. And then you're going to carry that acceleration to solving the other part, the missing distance. Don't worry, these equations are on the reference table. And you should get 120 meters for your distance. That's an example of a two-step problem where you're missing acceleration, but you need to find it before you can find the actual question's objective. Now, when you have so many equations, you need to figure out when am I going to use this. And there's two different scenarios you need to remember: constant velocity and acceleration. So that means constant velocity means no change in v, no change in velocity. And when you don't have a change in velocity, that means acceleration equals to 0. So all those kinematic equations will then simplify to this singular equation. This is our constant velocity equation, v equals d over t. On the other hand, if you do have acceleration, then you're going to use these suckers. My favorite one, my other favorite one, and then my least favorite one. You can see why. There's a lot of unnecessary stuff, or stuff I don't want to deal with. Anyhow. And now we finally reached the free fall section. So free fall, this means we're dealing with the vertical direction. So we're falling vertically. And this is where mass has no effect, air resistance is ignored. So if you see any mass, that means you don't need to use that. That's an extra piece of information. And here we got to make some assumptions. Acceleration due to gravity is a constant 9.81 meters per second squared. So this value doesn't change. It's a constant acceleration. But even though you have a constant acceleration, that means each second that passes, your speed increases. So your speed increases 9.81 meters per second every second that passes. So in the first second, you increase your speed to 9.81. In the second second, you increase it by another 9.81. And so your distance travel also increases exponentially. So that's what it means to accelerate. And so we have three different scenarios: dropped object, thrown down, and thrown up. Focus on the dropped object, that's the most common one, but thrown down and thrown up are kind of more relevant in the 2D kinematics unit, but dropped objects is very prevalent in this unit. So dropped object, if you think about you're holding an object above in midair. When you're holding it in your hand, it's not moving. And so when you drop it, its initial velocity is 0, and its acceleration is still 9.81 meters per second squared. When you throw an object down, when it leaves your hand, it has a velocity, so it's not 0 for initial velocity. Everything else is the same. And then thrown up, when you throw an object up, it also leaves your hand with a velocity. And once it reaches the peak of its motion, the height, the highest point it reaches 0. So an object reaches a stop the moment it hits the peak. So you throw an object up with a velocity, it slows down to 0 at the peak before coming back down as if it were a dropped object back into your hand. So what these three scenarios all have in common is essentially A is equal to 9.81 meters per second squared, except in the thrown up option, when you're going up, object slows down. So it might be easy to use negative 9.81 because it's slowing down, just for simplicity of calculations. All right, I'm probably going to have a separate video talking more about freefall, but this is more of a gist about freefall. And yeah, this is the end of the 1D kinematics video. I also have a separate video on motion graphs, so check that out, and I'll probably have a subsequent video about freefall and maybe relative velocity later on in the future. Ta-ta for now.